Hello and welcome. In this presentation, we will go over our final results for our final project, cancer prediction through CT scan imaging. This is Team 26, consisting of Batul Kader, Josh Matthew, and Shapam Dua. The motivation behind this project is that back in 2013, cancer was a leading cause of death after heart disease worldwide. And it is not limited to a single group, and it can affect different human tissues for people from different ages. One medical imaging method to diagnose cancer is CT scan or computed tomography, which captures a 360 degrees view of the tissue. The reason we want to do the project is that early prediction of cancer may help start an early and proper treatment of an early stage of the disease. Project task is to use deep neural networks to predict whether a given CT scan has contrast or not. Contrast is a dye to highlight the area to be scanned and examined. The first step we did was to filter out useless CT scans that can be further used to detect if a tumor is cancerous or not. The methodology we followed is that we trained a baseline convolutional neural network to classify CT scan images, and then we used transfer learning to optimize the model. We evaluated it through using accuracy.
We used a subset of the Cancer Genome Atlas lung adenocarcinoma dataset available on Kaggle as CT medical images. From the dataset, we took CT scans as tagged image file format to predict whether a CT scan has contrast or not. TIFF images are preferred in the medical industry because they are high quality images and do not lose their quality even after being edited multiple times. Our dataset consists of 100 CT scans, and from these 100 scans, we took 60 for training, 20 for validation, and the remaining 20 for test. We trained a simple CNN from scratch. The model consists of 2 convolutional layers and a fully connected output layer. Because our dataset is so small, we augmented some more data to our original dataset for the next 2 models.
Because of the small size of our dataset, we proposed using a transfer learning approach to try to achieve improved results by leveraging the knowledge gained from other image datasets. We used the exception and VGG models, which have been pre-trained on the ImageNet dataset. ImageNet is a very large image dataset consisting of over 14 million images from over 20,000 different classes. And the goal is to use the learned weights of the pre-trained models to extract meaningful features from our images and then classify our images based on those features. Below is the architecture of the VGG model. It's one of the state-of-the-art deep CNN structures, which has achieved very good results for image classification. We use this pre-trained model to extract a feature vector with 512 features from each image. We then trained a simple 2-layer fully connected neural network classifier from scratch to classify our images based on the extracted features. And VGG was trained on 3-channel color images, whereas our dataset consists of 1-channel grayscale images. So we stacked our 1-channel images 3 times in order to be able to feed them into the VGG model. And this is a common approach when using pre-trained models for grayscale images.
For the exception model, we started by doing some random data augmentation, such that we did random flipping for the images vertically, and we also changed the image contrast randomly. We used pre-trained exception model architecture, which is shown here, and this model is an extension to readily available trained model that's called Inception. The difference between the two is that the exception model has deeper convolutions than the other one. This shows here some of our model's losses summary. As we can see, the baseline model had the fastest and steepest learning curve, whereas the exception model didn't do as good as the baseline. The VGG model, as we can see, had some overfitting in the model.
Our baseline model, which was trained from scratch, actually achieved the best results in terms of accuracy on the test set, followed by exception and then VGG. The reason that the transfer learning approach maybe did not work as well, maybe because the ImageNet dataset, which VGG and exception were trained on, has a very different distribution of images compared to our medical images. And because of this, the features extracted by the pre-trained models may not be very meaningful for our dataset.
For our future work, we could improve the performance of the baseline model by using data augmentation to increase the number of training samples. We could also try using a different pre-trained model that has been trained on data that is more similar to our original data set, other than the VGG and the exception models, which are trained on the ImageNet models. Thank you.